So we talked about how we want to do structured prediction, but I sort of pulled a bunch of scores out of nowhere. So when we're learning features, how do we set the weights that allow us to make decisions about how to use those features? And so from a very high level, our goal is to make as few mistakes as possible. And a very intuitive way of trying to solve this problem is to punish features that cause us to make mistakes. This is a problem because the features are often correlated, and so any given example that we'd make a mistake on has many different features. How can we know which ones are the ones that we should punish? One of the earliest algorithms that tried to solve this problem was the Perceptron algorithm by Rosenblatt. And so this is a very old algorithm, but it serves as a foundation for a lot of modern machine learning. At every time step, you're going to receive some data point xt. Then you're going to compute your prediction for the label that that example will get. Then you receive the true label that the example should have. If your prediction matches the example, so that's getting us into this else clause here, then you do nothing, and so your weight vector remains unchanged. If you were wrong, then you add in your example weighted by the label to your weight vector. And so you're making the prediction based on the dot product of the weight vector and an example, and so if you get something wrong, then that will cause your predictor in the future to move in the direction that it should to get these examples right in the future. This looks a lot like many of the algorithms that we've already talked about. And so this loop over time looks a lot like SGD. You have examples, and then based on your prediction and the error that you make, you update your weight vector appropriately. It also looks a lot like the support vector algorithm because your weight vector is defined by a collection of points. And those points are the ones where you make mistakes. And just like support vector machines, the Perceptron algorithm will concentrate its attention on points near the margin. So we didn't start the class by talking about the Perceptron algorithm. It's very simple and it's related to a lot of the things that we talked about. The reason that we didn't talk about it is because support vector machines and logistic regression typically work better. But the ideas behind the Perceptron are very simple, and we can extend them to more complicated applications, like trying to figure out structured predictions. And there the intuitions work well, and it remains a fairly competitive technique. So how do we move from binary to structure? So let's again think about the binary perceptron where we're just trying to predict binary labels, either y is equal to -1 or +1. And so figuring out which label we assign to an example x is trivial. You just compute the dot product and see what sign it has. When you have a multi-class perception problem, that's still pretty easy. For a constant number of classes, you take several dot products and you see which one is the largest. The structured perceptron is quite a bit more challenging. And so here, you have an exponential number of classes, so you have to do things like dynamic programming when you can, but sometimes even that is tricky. And so doing exact inference is hard. We'll see why this is hard and what it does to the theoretical properties of the algorithm in a little bit.